20 requests.
Okay, let's start. Good afternoon. My name is Franco-Lespinasse, and today I will present our work that is about the status and developments of sputtered niobium onto copper quarter wave resonators here at Legnano. So first of all, this is the outline of my presentation. I will say some words about the research framework, the project in which we are participating. Then I will show to you the specific research aims of our project, the recent developments at LNL on this topic, and at the end I will say brief conclusions on our further works. So we are part of the OCAR project, and for this reason we are working in collaboration with CERN in order to find the best technique to deposit the quarter wave resonators, as Alban has presented before. So the requirements for CERN are cavities with accelerating field of 6 megavolts per meter and with a Q value at least of 510 to the 8. So our goal is to develop a magnetron sputtering configuration source to deposit quarter wave resonators for HIE-ISOLDE. But our specific research aims are to deposit a uniform thin film coating over the cavity to improve our superconducting properties. I'm talking about the RRR, and at the end to deposit and measure our first resonator here at LNL of HIE-ISOLDE type. So how to do that? We decided to use the magnetron sputtering technique. That is a very well-known technique. It has a main advantage, the higher deposition rate in comparison with another processes. But it has also a main disadvantage, the erosion of the material that is not so uniform. So that was our challenge. That's a magnetron sputtering vacuum system that we have developed here in the lab. On the left you can see the cross-section of our system with two main parts, the quarter wave resonator cavity and the double wall cathode that is inside. So in the first part of our procedure we were focused on the thickness of the cavity. We wanted to deposit the cavity uniform, the coating uniform along the cavity, so we decided to work with the stainless steel. So we built a cathode, a double wall cathode, as you can see in the slide, taking into account, of course, the shape of the quarter wave resonator and the inner conductor, of course. So for this reason we built also a stainless steel dummy cavity in order to deposit stainless steel onto copper quartz, as I will explain to you now. This the procedure that we use to deposit the cavities. That's the cross section of the quarter wave resonator, and we built a sample holder in order to place quartz samples along the cavity wall. The sample holder follows more or less the same shape of the cavity walls, and we deposit the stainless steel onto copper quartz. For this reason we have tested several configurations of magnetic field. Here I'm showing to you only the main result that we have got. So we did 7 runs with a pressure more or less around 10 to minus 3, 8 times to minus 3 millibars. The power was increased from 3 kilowatts till 10 kilowatts, and the time was from 30 minutes till 60 minutes. So it was our first result. This is a plot of the thickness against the sample position. It was not so good in the inner conductor and in the external conductor. As you can see, it's from 3 and 5 microns. But on the top of the cavity, we saw that we have a hole on magnetic field, so we decided to change the configuration. Also, we wanted to locate this place in which we didn't have the plasma, so we did a stripping test with the copper strip that we placed inside the cavity, and we saw that the problem was in between positions 10 and 12 on the top of the cavity. So for this reason, then we decided not to work with the thickness of the cavity, but also working in parallel, trying to deposit a good cavity, uniform film along the cavity, but also improving the superconductive properties. For this reason, we have built the niobium cathode. As you can see here, it was built with the same shape as before. It's a double wall cathode. And in this case, we performed 11 depositions with several magnetic confinements of magnetic field. So here I'm showing to you only the main results. In this case, the pressure was around 110 to minus 2 millibars. The power was increased from 3 kilowatts till 25 kilowatts. And the time was from 25 minutes till 30 minutes. And we had a parameter that was the heating of the cavity during the process. So it was our phase magnetic confinement. It was not so good because, as you can see, the thickness is not uniform at all. And the coating is lower than 2 microns. So we decided to change the confinement, the magnetic confinement. So this is the second magnetic confinement that we have tested. So we increased the thickness on the inner conductor, but in the outer conductor and also on the top of the cavity we had problems. So we decided again to change the configuration of magnetic field. So here we increase the thickness on the top, on the external part, and also in the inner of the conductor, and also in the fourth configuration of magnetic field. But we have the same problem, the top of the cavity. So for this reason, we have tested several configurations of magnetic confinement. Also, we did some simulations, and we put a viewport on the top of the cavity in order to see what was happening during the process. And fortunately, a new configuration have developed in order to increase the thickness, but also in order to improve the superconductive properties. So that's the result that we got. We had very good uniformity of the cavity, around 2 microns. But then we decided to measure the superconductive properties. We were measuring using the 4-point methods, and we got this. That's an interesting thing that we got, because that's a plot of the RRR against the power, and we saw that increasing the power, the RRR was increased also. That's a sample located on the external conductor, and the transition was around 9.3 Ks. So that's a very good result that we got in our lab. That's a plot of the TC against the RRR, and we got 61 in this position of RRR. So then we were interested also in the thin film morphology. Here I'm presenting to you the internal conductor. We saw that we had the grain size around 400 and 500 nanometers in the internal conductor, and in the external conductor we were not able to see the grain size, and for this reason we thought that maybe the heating was not so uniform, so we tried to manage this. So then we increased the thickness, we increased the superconductive properties, and we thought that we were ready to deposit our first resonator here at Leñaro. Taking, of course, into account all the experience that we got before with the stainless steel and also with niobium. So we performed our first deposition of the quarter wave resonator, the copper cavity, with these parameters. The power was 30 kilowatts, the sputtering pressure was 610 to minus 3 millibars, and the time was 40 minutes, only 40 minutes to coating our cavity. So we add to this process an important parameter that was the heating of the cavity during the process, which was 450 Celsius during the process. So that's the cavity. Before the coating, the quarter wave resonator, after the surface treatment that has performed at CERN, the chemical etching. And on the right side you can see the cavity deposit. This is our first quarter wave resonator. So Then we wanted to measure our cavity here in our lab, so we decided to work really hard to measure our cavity here in the lab. So we decided to follow all the procedure to measure the cavity. This is the high pressure rinsing of 100 millibars that was performed in our chemical lab. Then the tuning plate during the mounting of the cavity. And then we decided to build our cryostat that you will see maybe tomorrow in the tour, I don't know. But it was very good. We put down the cavity till 4.2 Ks and also till 1.8 Ks at the first time, so we are very happy for this. That's the RF system that we use to measure the cavity. The cavity was measured, and this was our first result. That's the plot of the Q against the accelerating field. The Q is not the best, it's below the CERN specifications, but the Q0 here is 210 to the 8. I think this is not so bad, so we are really motivated and we think that we can improve these results, maybe trying to decrease the distance between the cathode and the top of the cavity, as Alban has said. I think it was the same problem that CERN had before. Maybe to increase the temperature. Now we are trying to understand what happened with our process, but we are really motivated and we will try to improve our results. So the conclusions of my work: the cavity has been deposited with a good uniformity, around 2 microns. The superconductive properties, I'm talking about the RR, were increased, increasing the power. The first cavity of HIE-ISOLDE type has been deposited successfully at Legnaro. And also the test cryostat have been built here to measure our cavities. And then our further work is try to strip the cavity and deposit again and try to change the parameters in order to improve our results. I want to thanks to Walter Venturini for your advice, your help, and also Sergei Stark and Anna Maria Porcelato. Thank you.
So, questions directly to Daniel, or then we have time for a general discussion. Sarah?
You said a couple of times that you improved the RR. Did you mean increase or improve?
Yeah, we increased the RR, yes.
Why?
Because we start in our first deposition, we saw that along the cavity, the RR was something like 1 or 2 of RR. So increasing the power, we saw that along the cavity, RR was increased till 61. That was our best result.
See, yeah, that's exactly my point. I wouldn't consider RR 60 as the best result.
That we got, yes. No, I'm talking about our lab, yes. It's the best result
I'm
till now.
For the fact that you're operating at 4.5 Kelvin, so you want the lowest DCS resistance you can get, and this is RR 15, not 60. When you go to higher RR.
Q0, yes.
Yes.
But for the accelerated fit, it's not safe.
I think this is really what we should discuss in the general, because yes, it's true that the BCS is minimized at intermediate. But
in 2005, gosh, I presented the paper in Cornell workshop in which there is a dependence on the gap as a function of superfluid velocity, and this depends on the purity of niobium. And so according to this model, the minimum RR that you should have for the film is 100 if you want to improve the slope. So, I mean, one cannot believe to the model, but however, it's an open question.
okay, let's for the moment stop here. Any other questions on the presentation? Yes, Carl.
Do you have any idea where you have the losses in this test? You have some thermosensors?
Sorry?
Do you have any idea where you have your losses in this test? Or have you foreseen any additional equipment for detecting losses?
Really, why the Q is going so down? Yeah, this cavity was cleaned at CERN, and after Subu, we didn't get inside the cavity in order to measure the right distance. And in my opinion, we have done, how to say, this was a mistake, but however, we didn't want to contaminate the cavity. So the top distance is too big, because this is typical curve in which the radio frequency is going inside the copper. Now, what is our plan? Instead than stripping the cavity and going to do another coating, is just to take the cavity, to wash, to dry, and to coat over the old film on niobium. Maybe it will peel, but in the worst case, we will just lose one deposition.
And I strip it again,
But,
deposit again.
Stripping, I mean, we will do later also because we are not equipped for Subu, it will be a long time. So in another 2 weeks we will hope to measure again.
Okay, I think now in the program it is said that we should have 10 minutes of general discussion, so maybe if the speakers want to come up for 10 minutes, we can have a more global approach.